Welcome to our Lab Automation Masterclass. So I'm Marcus Gasheta. I'm co-founder and CSO here at Synthace, and I'm going to be your host. But I'm excited to introduce the gentleman who's actually going to be doing most of the work. Many of you may already be familiar with him from LinkedIn. That's Nathan Hardingham, who's an associate scientist here at Synthace. So Nathan's been here at Synthace for about a year, and he's immersed himself in automation DOE and the Synthace platform ever since, and he's keen to share some of his learnings so far. So thanks for doing this for us, Nathan, and I'll hand it over to you.
No worries at all. Thank you so much, Marcus. So to start off this talk, I'm going to take us all back to school, primary school, kindergarten, or your first ever science lessons. And in your first ever science lessons, you probably learn about liquids, solids, and gases. If you're a biologist, you probably don't worry too much about the last two, but I bet you know a lot about handling liquids. Throughout this talk, we're going to dive into some really specific automation and scientific principles. And to do that, I'm gonna give you some real quotes along the way of scientists that I've met, things I've seen online. The first one being, biology is pretty much just moving liquids around. And in my experience, this is more or less true. We occasionally put the autoclave on, but scientists and particularly biologists, we move liquids around. But the interesting thing is, we're damn good at it and without realizing. What I mean by this is, we adjust how we handle different liquids without thinking about it. So if a liquid needs mixing, we give it a mix. If a liquid is viscous, we chop off the tip. And if a liquid foams, we reverse pipette it. And we do this on pure instinct and experience. Unless you're living under a rock, you've probably heard of automation. And if you haven't, I'd strongly suggest you to check out the previous automation masterclass webinars in this series. You can find that on our Synthace YouTube channel, on LinkedIn. And what I mean by automation from a biology perspective is these liquid handlers and dispensers. I call them robots because it makes my job sound more interesting, but they're effectively just these brilliant bits of kit that move liquids around. So why are liquids difficult? Now, I love lab automation. The problem is the robots aren't always as smart as us. And I guess if liquid handlers are anything to go by, humans are safe from the robot apocalypse for at least a few more years. Jokes aside, they are brilliant, but they don't handle liquids as well as you do. And if you're pipetting water, cells, glycerol, protein, or detergent, you're almost certainly going to handle them differently. And if you're an experienced biologist, you do this almost subconsciously. So we're going to look at some tricky liquids you'll handle in your lab, and then I'll cover how we can teach our liquid handlers to cope with these sort of liquids a little later. So let's start off simple. Let's take ethanol, for example. It's a volatile liquid, and these sort of liquids tend to drip out of the pipette tip because the evaporating liquid causes the pressure to build up in the tip, and that causes the liquid to be expelled. You've probably encountered viscous liquids like glycerol. Honestly, these are hellish. Liquid drips out, air bubbles form, and it's difficult to fully expel all the liquid. Pipette manufacturers will tell us to never chop off the tip and buy their specialized kit and wide bore tips to handle these liquids. But yeah, we all know we're just going to chop off the tip. Then you've got these foaming liquids like Tween 20, PCR Master Mix. These liquids splash, build up in the tip, and bubbles can completely interfere with plate reading measurements and those transfers. And then you've got cells, honestly, about as intensive as looking after a 2-year-old, and cells tend to settle. So you have to gently resuspend your cells, dispense them slowly to avoid shear stress, and cells behave differently between cell lines. There's never a one size fits all way to handle them. And of course, some liquids can be even more difficult, and we can't treat all liquids the same, and we need to handle each liquid differently. Think about pipetting oils and DMS and maybe even genomic DNA and particulate samples. And some liquids just really don't play ball. So liquid handling can get very difficult very quickly. And honestly, at times, I've started to even question whether my liquids are liquids, which brings us on to another quote, and this time from the Synthace co-founder himself, Marcus. We enter the hellish corner of liquids where liquids aren't liquids. So moving to automation, and you've probably handled most of those liquids and you've adapted your technique subconsciously, but liquid handlers and dispensers, they currently don't do this subconsciously. And as of yet, those Hamiltons and the Tecans are not sentient. And I know some of the brilliant engineers who design some specialist hardware will be screaming at their laptops right now, but don't worry. I know there's some caveats to this and we'll get to that. But the bottom line is liquid handlers don't automatically adjust their liquid handling based on the liquid they're pipetting. And the thing is, when we move to automation, we now have to think far more carefully about liquid handling. And that's a struggle at times. A lot of us here today, like myself, will be biologists, biochemists, chemists, and many more disciplines, and perhaps don't have that expertise of automation engineers. Honestly, for me, it could be a little frustrating having to think now about how our liquids are handled and how we program our liquid handlers to cope. But sit back and relax, because today we're going to cover our experience of how we optimize our robots, cope with doing what we bought them to do, move liquids around. So what's a liquid class? And if you're familiar with automation, you'll know that robots can adapt the way they handle specific liquids, and they do this in the form of a liquid class. So what is it? Well, I mentioned when we use automation, we have to provide that liquid handling information to our robot. And I guess the funny way I always explain this was, let's say you're baking and you ask someone to measure out a tablespoon of water. They probably do this just fine. But now get them to measure a tablespoon of maple syrup. You want them to handle it differently because the syrup gets stuck to the spoon. Maybe you'd ask them to add some extra syrup to account for the loss in the spoon. Or maybe tell them to hold the spoon upside down for longer and let that syrup drip into the bowl. And maybe you'd let them lick the spoon too. But what you've done there is effectively you've created a liquid class. You've told your liquid handler to handle the liquid differently. So a liquid class is effectively the device-specific parameters that can be changed to affect how your device handles a liquid. And it comes in the form of this window on the right-hand side here. This is from Hamilton's Venus software, I believe, and I just had to include it because I love this retro Windows 98 aesthetic. But liquid handlers will also have this. And it's here that we can account for the liquid's specific properties, be it density, viscosity, surface tension, whether it forms clumps or settles at the bottom of a container. And why is it important? Why should we care? It directly affects accuracy and precision. If you didn't do this, you couldn't be sure that the correct amount of maple syrup was added to your mixture. Of course, this doesn't really matter too much when you're baking cookies, but imagine you're doing a highly sensitive, miniaturized biology experiment. It's crucial. And after all, one of the main selling points of moving towards automation, other than maybe that coveted walk away time, is because of the accuracy, precision, and repeatability. Let's be honest, liquid classes are a boring concept. Let's not pretend that tweaking a liquid class is on a scientist's bucket list. Why would we want to spend all that time tweaking something that we do naturally? Something that until automation was a thing we'd done without thinking. But once you optimize your liquid handling, not only will that experiment on the Hamilton, Fluent, Evo actually work, but you'll have confidence in your results. And you'll ensure that your result is true and not just noise due to poor liquid handling. Ultimately, it's the difference between your experiment working and not. And that gives us a great quote from Stephen Brown, who's going to be helping us out with some questions later. Once you crack your liquid class, everything falls into place. What's liquid class optimization? Why do we optimize? And what does optimization actually look like? Generally speaking, the idea is to test a different liquid class parameter to find an optimum liquid class for each liquid and, unfortunately, folks, on each device. So the general process is you run a small experiment with the liquid of which you want to optimize the handling, and run a series of experiments in which you modify the parameters of your liquid class, such as flow rate, and measure how that affects your response. And I'll explain what we measure in a minute. But the first question that I'd ask is, what do I change? What parameters in my liquid class do I change? Truly, there's not a one-size-fits-all approach, and it depends heavily on what you want to optimize. And why, and most importantly, what your use case is. If you have a highly sensitive assay like qPCR, where you're trying to quantify a sample, you're going to need to be as accurate and precise as possible. And maybe some protocols aren't as dependent on accuracy, precision, maybe construct assembly, where you don't need accurate quantities of reagent maybe for it to work. A lot of the liquid class parameters are more or less self-explanatory, but I'll explain a couple of the general features that are worth noting. The first is reverse pipetting, and this is a common technique you've probably done before with manual and automatic pipettes. And effectively what you do is aspirate more than you need and then only dispense down to the first stop. It's a really useful technique to prevent splashing and foaming because you don't have that blowout into the liquid. And you can usually achieve this on a liquid handler by setting an over-aspiration volume on your device. Then we've got liquid level detection and liquid level following. So liquid level detection is where the pipette tip detects that level in your liquid, and it does this by detecting changes in pressure or conductivity. And then that liquid level following is where the tip can follow and track that liquid level when aspirating dispensing. And we can see here on the right-hand side, this prevents that tip from being in contact with more of the liquid than it needs to be. So it stops those tips becoming overly coated in liquid and reduces that risk of carryover. In almost all cases, we probably want to do liquid level detection, but it's worth mentioning that if your plates aren't defined properly, your teaching's poor on your device, your liquid level will struggle as a result, because the liquid level following will take into account that geometry to dictate how the tips should move with the liquid during aspiration and dispensing. And if your liquid level detection relies on conductivity, then it'll do this by creating a circuit between the liquid, the plate, the device. And so if you use a plate like a PCR plate where the wells are raised off the deck, the device might struggle to form that circuit and therefore struggle with liquid level detection. But honestly, these features are worth playing around with, and particularly for your everyday liquids like volatile and viscous liquids, and really prevents those tips from getting coated in a sticky mess. Also worth mentioning, there's some very specific features for specific devices. And this isn't necessarily a liquid class parameter as such, but the Hamilton Star and maybe other devices have this too. And they have some additional functionalities, in this case for volatile or drippy liquids. And they have this anti-droplet control. And this feature is really cool. The pipetting channels effectively monitor pressure in the tip above the liquid level. And you can see with ADC on, they retract the plunger automatically to maintain that pressure in the tip. So when volatile liquid evaporates and the pressure increases, ADC will prevent the pressure buildup and prevent that droplet forming. And actually, features like this are really useful. Instead of having to tweak multiple liquid class parameters, if we have a catch-all solution like this, it can save you a lot of time. If you see features like this, do send them my way because they're really cool. So I mentioned some common categories of liquid, and we spoke about how we might handle them manually. So we just had to apply that logic to our liquid handler. So I've got some examples here of parameters that we might tweak for specific types of liquid. So we've got a volatile liquid. Usually we could add pre-wet cycles to increase humidity in the tip and prevent that pressure buildup, which ultimately leads to that droplet forming. We can increase flow rate to give the liquid less time to drip out the tip, and use filter tips due to vapor formation. We could also have a trailing air gap, and air gaps are these small volumes of air that could be either side of your liquid in your pipette tip, and they effectively stop the liquid from touching the instrument or being left inside the tip. And this is really useful for volatile liquids, and the air gap at the end of the tip will mean that the liquid's less likely to drip out during a liquid transfer. If we have foamy liquids, we can reduce the flow rate or aspiration speed. We can also reduce the number of mix cycles to stop that foam forming. And we also might want to rust pipette with foamy liquids. You also might want to avoid multi-dispensing, where you'd aspirate a larger volume of liquid and then dispense multiple times. Consider using a single aspirate and dispense. And certainly avoid reusing your tips, as that foam buildup can just be hellish. For cells, the most important thing to do is reduce that flow rate, because we want to reduce and avoid shear stress when aspirating and dispensing the cells. And we need to be really careful about contamination of other samples, but also the head and channels of the device itself. Filter tips are really a must when you're doing cell work. And then finally, for viscous, we'd almost certainly want to reduce the flow rate, have a slower blowout, and even touch off after dispensing to get all of that liquid off the tip. Viscous liquids are probably one of the trickiest, because we can get lower than expected transfers if we don't pause to allow that liquid to drip out the tip. But we also might dispense more than we intended if the liquid has adhered to the outside of the tip. So if we're planning to optimize our liquid class for a specific liquid or assay, this is a great starting point. But what do I measure? So the first way to measure, honestly, is to not measure. It's to eyeball. What I mean by this is that you should first just watch your experiment. By watching your experiment, you can see whether a liquid's dripping out of the pipette tip, whether it's bubbling when it's mixing, or develops liquid around that tip. After all, this is how we adjust our liquid handling when pipetting manually. It's based on experience. But I'd probably be asking yourself some questions when you're doing this. Is the tip submerging too far into the liquid? Do you get droplets forming on the tip? Is the dispense height too high? Are there droplets after dispensing on the tip? And from here, you can make reasonable conclusions. Remember, you're also going to be using the exact liquids that you intend to use in your protocol, unlike other methods I'll speak about where you might use a proxy liquid. So don't walk away from your experiment. I know there's more fun things to do, like watching paint dry, but when you're optimizing your liquid class, do take the time to do this first. Having said that, this doesn't provide any data on accuracy and precision. It's just a starting point. The next couple of options I'll show you are more targeted to assess the accuracy or precision. And if you're not familiar with those terms, accuracy is how close your measured value, like volume, is to the target value. So for example, the volume you intended to pipette, whereas precision is how close your measured values are together. A next step might be to use tartrazine. Many of you will be familiar with this. It's a cheap yellow dye, and it absorbs light at a specific wavelength. And if you use tartrazine, you can use this to optimize your liquid handling. And you use tartrazine usually as a proxy. So you're not actually measuring the sample or tricky liquid in this case. I believe it would be possible to mix your sample with tartrazine, provided it doesn't interfere too much with your absorbance measurements. So you can give that a go. And what you can do is create a known concentration of tartrazine and use your liquid handler to aliquot replicates of a specific volume onto your plate. Repeat this then with different liquid classes, and then measure absorbance, I think around at 400 nanometers. And then from your absorbance values, you can measure the coefficient of variation, for example, between your replicates. So this gives you a great indication of the precision you can achieve with different liquid classes. So the consistency of that pipetting. But if you want to truly measure precision accuracy, you probably want to get your hands on one of these, which is an MBS made by Artel. This device is incredibly powerful, and it can accurately and precisely measure liquid volumes, I believe, as low as 10 nanoliters. Effectively, what you do is mix their measurement dye with your liquid, and then aliquot your desired volume onto their Artel plate, and then top up with a second provided dye, and then use a plate shaker to mix the liquid, and then read the plate on the Artel. Artel have their own unique plates, which are compatible with most robot decks. So you can aliquot into these plates directly and then insert them. Generally, the intention, though, is to use their NIST-rated standards rather than your own samples. But I believe you can use their standards as proxies for your sample. So this can work really nicely. The neat thing about this is it gives you a digitized report of your results, and it's super granular. So if you're in contract research, somewhere where your methods are really under a lot of scrutiny, I think this is probably the best option. But Understandably, it's not a low budget option. Sadly, not the sort of thing that you can just put on your Christmas wish list. So a great option if you want to get thinking about your liquid classes the first time is these Check It Go cartridges. They're cheap and they're disposable cartridges, and they allow you to measure the volume of up to 8 channels at a time. Again, this is also compatible with most robot decks, so you can even pipette directly into the cartridge. These are intended to be used with their red dye as a proxy to measure the accuracy of your liquid handler or pipette, but they are compatible with various samples, I think like DMSO, glycerol, ethanol, albeit at low concentrations. Admittedly, the accuracy is not as impressive as the Artel, but considering their convenience, these are a really great way to get started with liquid class optimization. And the ability to use them on deck as well is super neat. So we now know what we're measuring or changing, how we measure it. So let's look at a experiment plan. So how do we actually put this into practice? Now, I know a lot of this sounds very laborious to undertake full experiments just to optimize liquid handling of one liquid, but your time saved will come from the experiments that either obviously fail because of poor liquid handling, or even from results that were unexpected or unreliable because you didn't take that time to optimize. And this quote from a scientist at LinkedIn, the best part is the time that you get back. And in my opinion, the best way to create an experiment plan that provides efficient and robust results is by using design of experiments, also known as DOE. It's a little off piece for the purpose of this webinar. You weren't going to get away with going to a Synthace webinar and not hearing about DOE. So I'll give you a very brief overview. So we traditionally run experiments by modifying one experimental factor variable, like aspiration speed, post-mix speed in this case, and then observe the response in an output factor like standard deviation or CV. On the other hand, DOE is the concept of planning an experiment which tests the effect of modifying multiple factors like aspiration speed and post-mix speed at the same time. All you have to do is choose your factors, choose a reasonable range of levels for those factors that you want to measure, and then use statistical software or Synthace to generate that DOE design. Usually this will pick a strategic subset of all the possible factor and level combinations to create that experiment. And hopefully that experiment will cover as many of these combinations as is required to understand the effect of manipulating those variables or factors. So it's great because you have to do less experimental runs because you can measure multiple variables at the same time. DOE is great. It provides a greater understanding of the individual, but also the combinatorial effects of modifying factors. And honestly, in my opinion, it's probably the gold standard way to find a true optimum liquid class. If any of those concepts are new to you, feel free to reach out to myself or anyone from Synthace. We would love to chat about DOE with you. So let's look at a case study and show liquid class optimization and DOE in practice. So in almost all experiments, you'd be handling liquids that aren't water. So we should tell our liquid robot rather to handle those liquids differently. So this is a really cool example of how we can optimize the liquid class for a specific sample. So I explained how you can measure the precision and accuracy of different liquid classes by measuring the difference between the target volume of an aliquot of liquid and the actual volume that's aliquoted. And you can measure that with an Artel or secondary bit of kit. But this example, which was done by our principal scientist, Nunu, does it a bit differently. Because he's far too clever for his own good, he uses the assay itself to evaluate the precision and accuracy of a liquid class. So instead of measuring the difference between target and actual volume of an aliquot of liquid, Nunu compares his manual execution of qPCR to an automated execution of PCR, and then tests that with many different liquid classes. If you're not familiar with qPCR, here's a very simplified explanation. And we use qPCR to quantify DNA in a sample. So if you combine DNA of a known concentration or your sample with a master mix, the master mix being a mixture of various reagents required for the PCR process, and then you can use a qPCR machine to get that result. And so in this protocol, what Nuno would do would be take 2 microliters of a known DNA concentration and combine it with 30 microliters of master mix. He'd do 4 replicates of this, stick that in the qPCR machine, and he'd get the output, which is a CT value. But what he'd do is he'd look at the standard deviation of that CT value between those replicates. And from there, he could get a gauge of the precision of that liquid transfer. So the aim of this experiment was to optimize the transfer of the DNA to the plate. So of course, we'd like to optimize the master mix transfers too. We couldn't do that in the same time because of run number constraints. So Nuno set out a plan to test how different liquid classes handle that DNA transfer. And so what he'd do is compare the standard deviation of those replicates that he achieved with the automated executions to his manually executed benchmark. Of course, we love DOE, so he used design of experiments to do this, so he can investigate multiple variables at once. So I've summarized the liquid class parameters, factors that he planned to investigate, and then the levels which he investigated for those factors on the right-hand side. From there, he created a DOE design to investigate those factors and their levels, and this resulted in 88 runs. These experimental runs would have 4 replicates. It's worth also mentioning, I've mentioned at the bottom, that he had to apply some constraints to his design. One of the factors, as you can see from the table, was extra aspiration. So that's an additional volume that's aspirated into the tip when transferring a liquid. And clearly, if you add extra volume to that tip that you didn't want to transfer, you wouldn't want to do a blowout or post mix, as that extra volume would then be added to your plate. So you have to think about some of these things. So after doing all of those 88 runs, including those manual benchmarks, he plotted this graph. This shows the average standard deviation of those replicates generated for each qPCR reaction, and then compared those to his manual execution. So each run, in this case, had a different liquid class, and we can just about see in purple on the right-hand side, the manual executions, which did have a very low standard deviation. For the most part, the automated executions had significantly larger standard deviations, which is not ideal, of course, but we can see that there were a large amount of runs that had very low standard deviations. And from that, we can assess the best liquid classes for this use case. I guess also worth noting, Nuno's a beast with a pipette. And in this example, the benchmarks had a very low standard deviation, and he still managed to improve the precision in a number of cases when moving to automation. So showing here the standard deviations for the 5 best liquid classes in comparison to that manual benchmark. And there was a number of optimal liquid classes that gave him the really low standard deviations. These are the most precise. And because he used DOE, not only would he know the liquid classes that performed best, but he could also find the most statistically significant factors, effectively those liquid class parameters that are worth fine-tuning. So things like mixing and aspiration speed, I believe in this example, were crucial factors. And this is really neat because it allows him to iterate. So if he had more time, I'm sure he'd probably fix the levels of factors that weren't statistically significant and then fine-tune the ones that were. A reasonable follow-on question would probably be, so if the optimal liquid class for the DNA transfer was found, could it be used for the master mix transfer? Yes and no. Nuno went on to test the standard deviations for 5 best liquid classes, and he used them for the DNA transfer and the master mix transfer, and then compared the results where he used those liquid classes just for the DNA transfer. So the ones in blue are those where the liquid class was used just for the DNA transfer, and then in pink is where those liquid classes were used for the DNA transfer and master mix transfer. Generally speaking, other than run 41, using that optimized liquid class for both the master mix transfer reduce the standard deviation. So sometimes, yes, the liquid class is transferable. So this is a really nice example of how we can actually do liquid class optimization. And maybe it's a slightly unorthodox way, but the results are really useful in showing that taking that time to optimize how the robot handles your liquids can really improve its precision. Now, forget everything that I just told you. So for the entire webinar so far, I've told you about liquid classes, why they're important, how we optimize them, but do we need them at all? There's going to be some caveats to what I'm about to say, but hear me out. What if we had liquid class agnostic robots? The robots that didn't need liquid classes. What if they could just handle any liquid with no fuss? So if you've got me on LinkedIn, you'll know I talk about this a lot. I promise I don't have a sponsorship deal yet. And the Dragonfly, it's a really cool bit of kit. It's a dispenser, so by design, it's not going to be moving plates around and transferring liquids, but it's incredibly powerful, particularly for assay development in drug discovery. So I asked some of the folks at SBT LabTech why it's liquid class agnostic, and they told me that their kit uses positive displacement syringes. So effectively means that the syringes move that liquid with mechanical force, moving in the direction of the liquid. And you can see in the video here, that liquid's in contact with that solid interface of the piston. It's really beneficial. And these syringes are also, I believe they're ultra low retention, so that mitigates the risk of those droplets forming. And what's really cool is that they can dispense simultaneously up to 10 channels. Really cool to see in action. So these syringes are neat and they allow it to achieve incredibly precise and non-contact dispensing down to nanoliters. They do offer some additional settings like reducing the dispense speed, which could be useful when handling like cells and viscous and foamy liquids. So I suppose in those cases, you could argue that it wouldn't be truly liquid class agnostic. And they'd probably be the first to admit that. But SPT LabTech feature in our next quote, where they claim they can achieve accurate and precise dispensing, irrespective of viscosity or environmental conditions. It's a pretty bold claim, and you can only really test this yourself, but from my experience, they are spot on. For balance, I will give you a second option, which is acoustic dispensing. Sadly, it doesn't look like this. Our lab manager, Francesco, using his favorite pipette, rather it looks like this. It's not some crazy Black Mirror episode, and this device, as you can see from the right-hand side, does move liquids with sound. And what it does is it focuses ultrasonic acoustic energy at the sample and ejects droplets into a second plate. And yes, that plate is upside down. This means it's not only non-contact, but it's tip-free. So I suppose you could say it's universally approved by turtles and fish. But Beckman say this device has dynamic fluid analysis. And what this means is that it can adapt to liquid properties on the fly. So it can simply adjust that acoustic energy that it requires for each liquid transfer without any human intervention. So this eliminates the need for a liquid class, but also treats every liquid independently. So before, when you had, I don't know, a glycerol liquid class, it might be 10% glycerol. So maybe it's not appropriate for 20, 30%. So this device adapts its dispensing method based on the actual liquid that's in the, frankly, it doesn't care what's in the well because it uses that bespoke setting every single transfer and adapts it. The final one I'll show you, and I saw this at Hamilton's Robotics Roadshow earlier in the year, and it's their Biofluidics BioSpot DX. Now, this takes a bit of a different approach. It's a non-contact dispensing system, but it uses optical imaging to analyze liquid droplets in flight. So you can see that on the right-hand side here, it's quite literally on the fly. And by doing this, it automatically calibrates based on the imaging of a single droplet's volume in flight. And so this calibration is done independently of liquid classes. And it can do all of this whilst dispensing 1536 wells in around 10 seconds. So yeah, the Usain Bolt of dispensers. And I just had to include this quote from Stefan Schork from Biofluidics. And I spoke to him at the Robotics Roadshow about this device. And after his brilliant demo, myself and many others kept asking him about liquid classes. And understandably, he came out with this quote: "Forget about liquid classes." And I love that. Of course, take what I've said with a pinch of salt. I know these are dispensers, so they're not suitable for every application. Having said that, it shows a world without liquid classes is possible. So there's hope, people. And with that, I will wrap up with a little summary. And I think the main take home is that not all liquids are water, and optimizing your liquid classes is boring. I appreciate liquid class is not the most glamorous and sexy part of science, and you've got far better things to worry about than liquid classes. But that's the point. If you ignore liquid classes, your experiments will pay the price, and you won't be able to ensure the precision, the accuracy, and the confidence of experiments. Remember, when you're optimizing your liquid class, honestly, the best part is the time you get back. Very shameless plug to connect on LinkedIn, not just myself, but Marcus and Steve, who's going to be helping to answer some questions. But the purpose of this webinar isn't to tell you how things should be done. It's to start a conversation. And if you have questions, you want to tell me that I'm talking absolute rubbish, let's continue that conversation and discussion on LinkedIn. We don't take ourselves too seriously. We're always up for discussion, debate, maybe a bit of criticism here and there too. So with that, I will leave you with my final and perhaps most inspirational quote of the day before we dig into some questions. A nod to Ron Burgundy if you've watched Anchorman. Stay liquid classy. Thank you very much for spending your Wednesday with me. Have a lovely week, and we'll jump into some questions. Thank you.
Thank you very much, Nathan. So yeah, we've got some questions coming through. So thank you to our audience. So while we give everyone a chance to ask a question, I just wanted to talk a bit about some additional resources with you. Many of you will be familiar. This isn't our first Masterclass series. We started off with DOE Masterclass last year. We've got 11 sessions on demand available on our website. The link is in the chat if you'd like to check that out. And if you're looking for a more sort of high level DOE training, which is about to launch a new DOE training email course, where Sid and Jar Jar from our team are going to teach you about the DOE fundamentals in under 6 minutes a day. Okay, so that was brief plug. Before we jump into questions, I'm excited to introduce a special guest for our Q&A. So that's Steve Brown. He's a senior research scientist here at Synthace and one of our resident liquid classes experts. And given how much Nathan's said that liquid classes are dead boring, I'm sure he's massively offended at this point. Anyway, hi, Steve.
Hi, everyone. Hi. I'm not that offended.
So yeah, and just to say, if we don't get to your question in the session now, because we often get quite a few questions, then we'll look to follow up with an answer after the session. First off, we dive in straight with the tricky ones. So how transferable are liquid classes from device to device?
Yeah, so I guess I can take this one. I touched on it a little bit. It's a tricky one to answer. And I think that the purists would say you need to optimize every concentration of every liquid on every device. And you can't even transfer that liquid class to a duplicate device within your own lab. And bear in mind, not all devices have the same liquid class parameters, where the Hamilton star maybe had the anti-droplet control, maybe another device didn't. But in some cases, they are transferable. And we showed with the qPCR example, the liquid class for that DNA was somewhat transferable to the master mix. But it's not always the case. But honestly, I think ultimately you can get a gauge of the important parameters and the parameters that are significant and have a significant effect. And those parameters would be usually transferable. And so you get a good gauge and a good starting point from there. Hope that answers your question.
Yeah, absolutely. And I think, just to comment there, I as with so many things, I think it's highly multifactorial, isn't it? Depending on exactly what liquid it is and what kind of plate you're dispensing or pipetting out of into whatever plate you're going into. There's so many different things which can lead to variability from class to class, but absolutely there tend to be the same kind of factors popping out and things for the same situation. Steve, did you have anything else to comment on that?
Yeah, I would just like to say we released protocols through the Synthace platform that people can use. And we used to say things with device agnostic. so they'd work on any device. And the liquid class aspect is something where things become very device specific, but not too different. As you say, the main learnings of what you should change for a particular liquid type remain the same. And so for example, the qPCR example that was given by Nathan, thanks for that, was actually done also on the Tecan Evo and the Gilson. And we looked at comparable results across those liquid handling platforms to be able to give us something better than manual execution. And so through Synthace, we provide those as things that you can just get on and use to make sure that your quantification using qPCR is as accurate as possible. Yeah, so we do a lot of work on trying to transfer things through multiple devices.
Yeah, we spend a lot of time at that kind of thing in the lab. Second question then, in your experience, what proportion of time does it take to optimize liquid classes when developing an automated protocol? So I think I'll direct that one straight at Steve because I know we've done a lot of this.
Yeah, what we've done here, as I said, the qPCR example was done on those 3 devices. And I'd say going from something like getting the reagents to writing everything up and making sure that knowledge is transferred, something like that, it would probably be proportionally like a quarter of the time. I say proportionally because things change with complexity in how much you do. But if you say that was 3 devices, so you said maybe a third of your time, a quarter to a third is about what you'd expect to do when you're developing like a new protocol for automation in our experience.
Yeah, and I guess it just depends on, how evil the liquids are that you're actually transferring. And actually, we've got another question talking about another level of complexity about dispensing different volumes, large volumes versus low volumes of each liquid type. And the behavior can be quite different. And how would we deal with this? And honestly, from all our experience, and I'm sure Steve got some comments here as well. Yeah, different volumes make enough of a difference that you have to re-optimize. You can't just assume that because you can pipette 20 microliters of glycerol, you can pipette 2 microliters of glycerol.
Yeah, I think sometimes we've been guilty at trying to miniaturize things too much when we could actually look at changing other things like the device type we run something on to get better behavior, or adding something less concentrated so that we can increase the volume, go below a threshold. So sometimes you're being guilty of trying to force things too low as well. And I think so just be wary of that. It's nice to know those thresholds of behavior for your devices and design your experiments, the protocols to adhere to that.
Yeah, I guess this goes a bit meta then, doesn't it? Because it's not so much about what liquid class is best to get best precision, but it's like, what is your overall experimental design which gives you best precision? So just to unpack what Steve was talking about there for a second, if you have a total volume of 10 microliters in a thing and you've got 2 things to add, then you might think of doing 9 microliters in 1 microliter, but it would make an awful lot more sense if you can to do 5 and 5 and alter the concentrations of those stock inputs so that actually you're just going to make yourself that much more likely to get that higher level of precision in the first place. So that's a really good point. And now we've got a bit of a deeper question now, more specifically around the Synthace platform. So this is obviously a Synthace user. So liquid class and liquid policies are pretty hidden on the Synthace platform. And I haven't seen an easy way to do a DOE to optimize that. How would you handle a liquid class optimization through DOE on Synthace? So first off, this is a really interesting one because often this is the kind of thing where we would want the automation experts and that kind of thing to do these optimizations. So then most people using Synthace don't have to worry about these kind of aspects of the workflow. So in some ways, it's a deliberate choice to have these things not exactly front and center when we're doing things. There are ways of doing liquid class optimization DOEs. That's exactly how Nunu did it. It was on the platform. It isn't something that, we've made exposed very highly, and it's not exactly the most amazing kind of user experience, I don't think, of doing that, if I'm brutally honest. But at the same time, it allows you a very powerful way of very rapidly optimizing your liquid classes. With that, I think we'll say thank you very much to both Steve. Thanks for dropping on and giving some more information and the benefit of your experience. And thank you very much to Nathan for putting this webinar together and taking us all through this today. It's been very helpful indeed. To everybody who signed in, look forward to seeing you at the next automation webinar, which, as I say, they go out on the first Wednesday of every month. So thank you very much for your time today, and I'll see you at the next one. Bye.
Bye, everyone.